Hi and welcome back. This is Spectre P and we are Spectre AI. In the previous video, we built a working binary quantum state discrimination pipeline using explicit state preparation, measurement, and decision rules. In this video, we go one level deeper and ask a more fundamental question. Given two quantum states and fixed prior probabilities, what is the best possible measurement we can design, and how low can the error probability ever be? Answering that question leads us away from ad hoc measurement choices and toward optimal measurement theory, culminating in the Helstrom bound, which sets the absolute limit on binary quantum decision-making. We begin by stating the problem precisely. A quantum system is prepared in one of two possible states, which we denote by rho 0 and rho 1. These states are not assumed to be orthogonal, and they may overlap in Hilbert space. Each state is prepared with a known prior probability, P0 or P1, reflecting how often each hypothesis occurs. Our task is not simply to perform a measurement, but to make a decision about which state was prepared, based on the outcome of that measurement. Every incorrect decision contributes to an overall probability of error. The central objective is therefore to design a measurement and an associated decision rule that minimizes this error probability. Framed this way, binary quantum state discrimination becomes a constrained optimization problem where physical measurement rules limit how well any decision strategy can perform. We can now write down the quantity we are trying to minimize. The probability of error is defined as the total probability of making an incorrect decision, averaged over the prior distribution of states. If the system is prepared in state rho 0, an error occurs when the measurement outcome leads us to decide in favor of hypothesis 1. If the system is prepared in state rho 1, an error occurs when the measurement outcome leads us to decide in favor of hypothesis 0. The total error probability is therefore the sum of these two conditional error probabilities, weighted by their respective priors. What is critical to understand is that this error probability is not a fixed property of the quantum states alone. It depends explicitly on the measurement we choose and on how we partition the measurement outcomes into decision regions. Geometrically, this corresponds to selecting a boundary in state space that separates outcomes associated with the two hypotheses. Different measurement choices induce different decision boundaries, and those boundaries determine how much probability mass from each state falls into the wrong region. This immediately tells us that measurement choice is an algorithmic design decision. There is nothing privileged about measuring in a particular basis unless it happens to minimize this error functional. The problem of binary quantum state discrimination is therefore not about extracting information from a system in some absolute sense, but about designing a measurement that optimally balances the overlap between states against their prior probabilities. This framing sets the stage for asking whether there exists a measurement that minimizes this error probability globally, and if so, what fundamental limit that minimum must obey. What this comparison illustrates is that the probability of error is not an intrinsic property of the quantum states alone. The same pair of states, prepared with the same prior probabilities, can produce different error rates depending entirely on how the measurement is chosen. In the left configuration, the measurement effectively partitions outcome space along an arbitrary axis, creating decision regions that capture a substantial portion of each state's probability distribution on the wrong side of the boundary. Those regions contribute directly to the error probability. In the right configuration, the measurement basis has been rotated. The quantum states themselves have not changed, and neither have their priors, but the decision boundary is now better aligned with the geometry of the states. As a result, less probability mass from each state falls into the incorrect decision region, and the overall error probability is reduced. The key point is that nothing about this improvement comes from additional information or more data. It comes purely from measurement design. This demonstrates that measurement choice is an algorithmic degree of freedom. There is no privileged or default measurement that minimizes error in general. Instead, the measurement must be designed to balance state overlap against prior probabilities in an optimal way. Once this is recognized, the problem naturally becomes one of optimization. Among all physically allowed measurements, which one minimizes the probability of error, and what is the smallest error that any measurement can possibly achieve? That question leads directly to the concept of optimal measurements and to the fundamental bound that governs binary quantum decision-making. At this point, the problem has a precise mathematical structure. We have an explicit expression for the probability of error, and we have seen that this quantity depends on how the measurement partitions outcome space into decision regions. The remaining question is no longer whether measurement choice matters, but which measurement minimizes the error probability over all physically allowed measurements. From a geometric perspective, each admissible measurement corresponds to a particular decision boundary in state space. As that boundary rotates, the probability mass from each quantum state that falls into the incorrect decision region changes continuously. Most of these boundaries are suboptimal, in the sense that they allow unnecessary overlap between the states and the wrong decision region. Among this family of possible measurements, however, there exists a special choice that minimizes the total error probability. This observation transforms binary quantum state discrimination into a well-defined optimization problem. The objective function is the probability of error, and the variables are the measurement operators themselves, subject to the constraints imposed by quantum mechanics. Importantly, the optimal measurement is not defined by convenience, symmetry, or a preferred basis, but by the solution of this constrained minimization problem. The decision boundary labeled here as optimal is distinguished not by intuition, but by the fact that no other physically realizable measurement can reduce the error further. This framing is critical, because it tells us that optimality is a mathematical property, not a heuristic choice. Once the problem is posed in this way, the remaining task is to characterize the measurement that achieves this minimum and to determine the value of the minimum error itself. The solution to that problem leads directly to the concept of optimal quantum measurements and to the fundamental bound that governs how well any binary quantum decision process can perform. At this stage, the optimization problem can be solved constructively. The key object is the operator defined as the difference between the two hypotheses weighted by their prior probabilities, commonly called the Helstrom operator. This operator encapsulates both the geometry of the quantum states and the asymmetry introduced by the priors. Rather than searching over decision boundaries directly, the optimal measurement is obtained by analyzing the spectral structure of this operator. The Helstrom operator is Hermitian, which means it admits a complete set of orthogonal eigenvectors with real eigenvalues. These eigenvectors define a preferred measurement basis, not because of symmetry or convenience, but because they diagonalize the operator that governs the error functional. The measurement corresponding to this eigenbasis partitions outcome space into two regions associated with the positive and negative eigenspaces of the operator. The decision rule is then simple. Outcomes corresponding to positive eigenvalues are assigned to one hypothesis, while outcomes corresponding to negative eigenvalues are assigned to the other. Geometrically, this construction defines a decision boundary orthogonal to the Helstrom operator's eigenaxis. That boundary is not chosen arbitrarily. It is fixed by the operator itself. Any other measurement corresponds to projecting onto a different basis, which necessarily mixes positive and negative components of the operator and increases the probability of error. In this sense, the eigenvectors of the Helstrom operator uniquely define the optimal measurement for binary state discrimination. This result is powerful because it converts an abstract minimization problem into a concrete prescription. Once the Helstrom operator is constructed, the optimal measurement follows directly from its eigenstructure. There is no remaining freedom to tune the measurement without increasing error. This provides both a theoretical characterization of optimality and a direct pathway toward implementation, which is what allows optimal quantum decision strategies to be realized explicitly in algorithms and circuits. Once the Helstrom operator has been constructed, the optimal measurement follows directly from its spectral decomposition. The key step is to diagonalize the operator and identify its eigenvectors, which define the measurement basis that minimizes the probability of error. Rather than measuring the input state directly, the system is first transformed into this eigenbasis. Conceptually, this corresponds to rotating the state so that the Helstrom operator is diagonal with respect to the measurement axis. After this basis change, the measurement itself is completely standard. The system is measured in a fixed computational basis, and the outcome is interpreted according to the sign of the corresponding eigenvalue. Outcomes associated with the positive eigenspace are assigned to one hypothesis, while outcomes associated with the negative eigenspace are assigned to the other. No additional optimization or thresholding is required at this stage because the decision rule is already encoded in the structure of the operator. What is important here is that optimality is achieved entirely through the choice of basis. The measurement hardware does not need to be modified, and the procedure does not depend on ad hoc tuning. All of the complexity is absorbed into the construction and diagonalization of the Helstrom operator. This makes the optimal measurement both theoretically well-defined and practically implementable, reducing the problem of optimal quantum state discrimination to a sequence of linear algebraic steps followed by a conventional measurement. At this point, the optimal measurement can be implemented directly. Once the Helstrom operator has been constructed and diagonalized, the problem reduces to a simple change of basis followed by a standard measurement. The role of the unitary shown here is to rotate the input state into the eigenbasis of the Helstrom operator. This unitary is not arbitrary. It is determined entirely by the eigenvectors associated with the positive and negative eigenspaces of the operator. After this basis change, the measurement itself is completely conventional. The system is measured in the computational basis, producing one of two possible outcomes. These outcomes are then mapped directly to decisions. Measurement results associated with one eigenvalue correspond to deciding in favor of the first hypothesis, while results associated with the opposite eigenvalue correspond to deciding in favor of the second. The decision rule is therefore encoded in the sign structure of the operator, not in any additional post-processing. What is important to emphasize is that all optimality has already been enforced before the measurement takes place. The circuit does not attempt to minimize error dynamically or adaptively. Instead, the minimization is built into the choice of basis. Once the correct unitary is applied, the remaining steps are deterministic and straightforward. This shows that optimal quantum state discrimination does not require exotic measurement primitives. It can be realized using a small number of elementary operations followed by a standard projective measurement. This construction makes the Helstrom measurement both theoretically optimal and practically executable. It also provides a direct bridge from quantum detection theory to algorithm design, where optimal decision-making is achieved through explicit circuit structure rather than heuristic measurement choices. What's shown here is a numerical verification of the optimal measurement we derived theoretically. Starting from the two quantum states and their prior probabilities, we explicitly construct the Helstrom operator as the weighted difference of the corresponding density matrices. Diagonalizing this operator gives us its eigenvalues and eigenvectors, which define the optimal measurement basis. The unitary, labeled here, simply rotates the input state into that eigenbasis. Once that rotation is applied, the rest of the procedure is straightforward. The state is prepared using a single rotation, the basis change unitary is applied, and a standard computational basis measurement is performed. No additional optimization is required at this stage because the decision rule is already encoded in the structure of the operator. the measurement outcomes are mapped directly to decisions according to the sign of the associated eigenvalue. The key result appears on the right. The observed probability of error from repeated circuit execution converges to approximately 0.249, which matches the theoretical Helstrom bound of 25% for this problem up to finite sampling noise. This confirms that the circuit is implementing the optimal measurement and that the minimum achievable error is being reached in practice. The agreement between theory and simulation demonstrates that optimal quantum decision strategies are not just abstract bounds, but can be realized explicitly with simple circuits and standard measurement operations. This result has important implications that go well beyond the specific example we just analyzed. First, the Helstrom bound represents a true optimal performance limit for binary quantum decision-making. Once this bound is reached, no algorithm, no measurement strategy, and no experimental refinement can reduce the probability of error further without changing the problem itself. In that sense, the bound plays a role analogous to a physical speed limit, defining what is fundamentally achievable rather than what is technologically convenient. Second, this optimality has direct consequences for security and robustness. In cryptographic and sensing applications, the Helstrom bound characterizes the best possible performance of an adversary, attempting to distinguish between quantum states. If a detection strategy saturates this bound, then any attacker or eavesdropper is already operating at the theoretical maximum allowed by quantum mechanics. Improvements in hardware or signal processing cannot bypass this limit. Only changes in the underlying protocol or assumptions can alter the outcome. Finally, the Helstrom bound provides a meaningful benchmark for quantum algorithms. It separates genuine algorithmic improvement from apparent gains that arise from suboptimal baselines. When evaluating quantum classifiers, hypothesis tests, or decision procedures, comparison against the Helstrom limit reveals how close an approach comes to optimal performance. This makes the bound a reference point for assessing whether an algorithm is fundamentally efficient or merely heuristically effective. Taken together, these implications show that optimal quantum state discrimination is not just a mathematical curiosity. It defines a boundary between what can and cannot be achieved in quantum decision processes, shaping how algorithms are designed, how security is evaluated, and how performance claims are interpreted. The analysis we've presented applies specifically to binary quantum state discrimination, where only two hypotheses are involved. In that case, the problem admits a closed-form solution. There exists a single optimal measurement that minimizes the probability of error, and that measurement can be constructed directly from the Helstrom operator. This makes the binary case mathematically complete and conceptually closed. Once we move beyond two states, however, this structure no longer holds. When three or more non-orthogonal quantum states must be distinguished, no single decision boundary can optimally separate all hypotheses at once. The geometry becomes fundamentally more complex, and there is no longer a unique projective measurement that achieves minimum error in closed form. As a result, the techniques that work so cleanly in the binary case do not generalize directly. In these multi-state settings, optimal discrimination typically requires generalized measurements known as POVM, or adaptive and sequential strategies that exploit additional structure in the problem. In some cases, different optimality criteria must be considered, such as unambiguous discrimination rather than minimum error. The key takeaway is that binary discrimination represents the simplest, non-trivial case in quantum decision theory, and understanding it fully provides the foundation for tackling more complex scenarios. By seeing both the solvable case and its limitations side by side, we can better appreciate where exact solutions exist, where approximations become necessary, and why the Helstrom bound occupies such a central role in quantum detection theory. We can now summarize the full structure of binary quantum state discrimination from first principles to execution. Starting from the geometric representation of two non-orthogonal quantum states, we formulated the problem as one of minimizing the probability of decision error rather than estimating state amplitudes or observables. That objective led naturally to the construction of the Helstrom operator, which combines both the state geometry and the prior probabilities into a single Hermitian object. Diagonalizing that operator revealed the unique measurement basis that minimizes error, and implementing the corresponding basis change reduced the optimal measurement to a simple unitary rotation, followed by a standard computational basis measurement. Numerical simulation confirmed that this procedure achieves the Helstrom bound, demonstrating that the minimum achievable error is not just a theoretical limit, but an operational one that can be reached with explicit circuits. The key takeaway is that binary quantum discrimination admits an exact optimum. Once the Helstrom bound is reached, no further improvement is possible without changing the underlying problem, such as altering the priors, the states themselves, or the cost function. In this sense, the Helstrom bound plays the same role in quantum decision theory that fundamental limits play elsewhere in physics, separating what can be optimized from what is fundamentally constrained. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.